All right. I'm basically going to talk about the same stuff that Doug was talking about, just in a little bit more detail. And if you have any questions or comments, which I'm sure there will be, just interrupt me at any time. I think there's a lot to talk about. I try to make it slow, but I have a tendency to speak fast, so whenever I'm too fast, just tell me and I'll just try to slow down. Okay, so this is just a point that Norm was making. Imagine that this would be the model space that we have, and each of the published GMPs is just a point in model space. This is just some random space that I draw. You can think of it as just a 2D model space, and each GMPE is a point on that model space. And these are just the published GMPs. But what we're assuming is that there are many unobserved GMPs. Just imagine if you had done the NGA project with 10 development teams instead of 5, you would have 10 different GMPs instead of 5. And if you had like more data, there would still be different GMPs. And the question is, can we capture the center, body, and range of the unobserved GMPs only with the observed GMPs? So basically, how can we go from the red dots, which are the unobserved, the observed GMPs, how can we come to the gray dots? And the assumptions that we're going to make is just that GMPs are a sample from a underlying distribution of models. So each model is a sample from a distribution of models. And then the only thing that we have to do is we have to capture this distribution of models. All right. And so this is basically the fundamental approach that Doug pointed out. We take the selected GMPEs. We fit each GMPE to a common functional form. Then each of these GMPEs will have its own set of parameters of the common functional form. And then from these sets of parameters or coefficients, we can estimate the joint distribution of the coefficients, and then we're going to sample from this joint distribution of coefficients. And that way we can sample new GMPEs. We can estimate, so we can go from a sample to a distribution, and then we just sample from that distribution. And in the end, since we sample a lot, like 1,000 new GMPEs, we somehow have to reduce the model space. So we have to say which ones are likely, which ones are unlikely. And I'll try to point out how that might be done. So this is just the thing slightly more formal. So basically, each GMPE M is a sample from some underlying distribution F. And in general, if you think of all the complexities that can occur, this will be a very, very complicated distribution. And it's probably nothing parametric or anything that we can capture. But the way we can try to capture this is that if we assume that all models have the same functional form, then this distribution F, that is the distribution over GMPEs, will become a distribution over parameters, over the coefficients of the GMPEs. So, and then if we make further assumption that this is a multivariate normal distribution, then we can actually work with that. That's not necessarily, might not be a good assumption, but this is a very simple thing that we can easily work with. So basically what it boils down to is estimate these coefficients theta of each for each model, calculate mean and the covariance of these parameter sets, and then sample from them. Right, so this is just the same thing as I said before. Fitting, calculating mean and covariance, basically calculating the correlation of the different parameters, and then sample new sets of coefficients, and basically sample new sets of GMPs.
I just want to interrupt you a few times so that we make sure. So is it clear to people what he's doing right now? So how is he generating the 1,000 models? So I'm seeing some yeses. Okay.
I will come to that
We'll come to
when
that.
I show,
Okay.
show the example.
So, but the concept, right, he's going to take a form. When he fits everything to that form, now coefficient C1 is the same for every GMPE. Coefficient 2 means the same thing. In our published models, they're all different, right? And so we can't compare coefficients. Now he can compare coefficients and, in fact, build a correlated model of how those coefficients vary. When C2 goes up, C3 has to go down, right? That's his whole thing that's going on here. Rob, did you have a question?
Okay, so that is clear in terms of the process. What I'm a little unsure about is the sampling that's done in a random sense, and are there any parameters on that randomization other than just adhering to this correlation structure?
No, and this is probably something I need to work, or we need to work on, is just impose restrictions on some of the parameters to avoid certain. You will see that there are some models which are just unphysical, and we can either throw them out or we can just assure that this doesn't happen. Problem is, if we want to impose restrictions on the parameters, we need to be careful with the correlation structure and the covariance, because it messes things up a little bit.
It's more difficult, but we do have to get there so we don't generate
that's right.
unphysical models. I think that's what Yusuf was talking about earlier.
So, Nico, can you go back to previous slide, please? Okay. If maybe you're going to explain later. It's not clear to me that if the functional forms are not the same of the seed GMPs, what you're going to do. That's maybe you're going to elaborate.
Yeah, they're not the same, but I mean, each GMPE has a certain structure that is overall similar. So
they all look like a point source stochastic model fundamentally, with a linear or quadratic magnitude term, a magnitude-dependent geometrical spreading, and a log R plus a constant, right? And then at large distances, a linear R term. That gets you most of the way there.
Well, the way that you just said, that's correct, but BSSA, they use RJB, for example. And on top of the hanging wall, we know that they're different than the others. If we just exclude that uniqueness of GMP, they become too close to each other. So I'm pretty sure overall,
the only problem is really, well, the main problem is RJB versus RUP. So that really, you will see that when I show the residuals of the GMPs to the common functional form. They are, I mean, they are not zero, because the common functional form is different than the functional form of each GMPE. But the residuals are small. They are slightly larger for the BSSA model because it has RJB and I'm using rupture distance. But you will also see that it's close, and then Nick calculated hazard using the original BSSA model and the fitted functional form, and the hazard curves are close. Are really close.
Definitely is the sanity check that we have to see the final results. That's a very good point. But intellectually, fundamentally, I just want to make sure the advantage of this is that you use these multiple bases. It's like, the way I see it, it's like eigenvectors, and you generate the whole space. Then that is a good part. But suppose one GMP has some unique thing. Somehow we have to preserve. Maybe we don't know it now, but we have to preserve. Hypocentral depth is another example. Sorry.
If you want to include that, nobody is forcing you to like exclude that. This is just if you say I'm not capturing what I want to capture with this approach, you can just bring it along, you know. And I'm not saying just put, I'm not saying take this as an algorithm, take the numbers out, and then just run that as you need to check and check and check every time, whether it makes sense or not, and then maybe go back or bring something new along. Okay?
Okay, I have a couple of questions. Well, actually, along these same lines, have you thought about using a functional form that is a little bit more general than the CY functional form?
Actually, my favorite functional form, well, my favorite thing would be something non-parametric.
Oh, yeah,
The
Gaussian.
nice thing is because, I mean, we can generate data. So we can generate data in the regions where we want to do that. And so we don't need to worry about extrapolation, which is the problem with the non-parametric things is it's difficult to bind them into something joint. You know, it's difficult to like extrapolate in model space. I have some ideas, but I need to think about that. So my favorite thing would be a Gaussian process, because the Gaussian process is a distribution over function. And this is the distribution over function, right? But it's not so easy to get to that distribution.
Okay. Yeah, the other question is, I don't know with the number of GMPs you have, if that makes sense, but if the marginal distributions of the C's were non-normal, you might want to do a transformation and then create a covariance matrix of the transform quantity. But on the other hand, with 5 or so GMPs, you may not be able to see any distribution shape information.
That's right. So one of the simple things you could do is you could just, I mean, you can interpolate between the GMPs, like take 50% one to 50% the other, so 0.5 times 1 plus 0. This will give you a new GMP. You fit the same common functional form, and then at first you interpolate, you fit, and then you extrapolate. All in GMP space now, so not in terms of magnitude or distances. I think this is probably a better way to do that, to constrain the covariance between the models.
So that you get more models to define
exactly.
the covariance structure
right now,
better. Okay.
I mean, I'll show examples for the strike slip case, and we have 7 GMPs in the beginning. And it would be nice to broaden that out to something more so that we can get a better estimate of the joint distribution of the coefficients. That's right.
So let's let Nico go, but I want to make sure this step is clear. So just, he's creating new models from a common form, and we'll get to what that common form is. Right?
It's also, it might not be the best common form that there is. So I think Brian pointed that out. So Brian's model is fairly, it's a bit more complicated. It looks more complicated because it has all these hyperbolic terms in there, but it is a bit more general. So it's a bit more flexible than what I'm going to show here. But also, I'm not so sure about the distribution of the parameters for his model, if that is really joint normal.
That's his big assumption there on the bottom, right? That he could, those things are distributed normally is his fundamental assumption, and that's where we can, we're using that to extrapolate those GMPE space.
So there, that might be a place where kind of subjectively based on physics, for example, you may be able to introduce some transformation. For example, some coefficient that you don't want to be negative. You may put in some constraints, which may be in the form of a distribution transformation.
So it's a bit more complicated to do that in the framework of a joint normal distribution, but you can do that.
But again, you can do a transformation and then make the normal assumption on the transform quantity, like say log normal in the simplest case.
So when you say the parameters are normally distributed, do you mean log normally or normally?
No, in this case, I mean normally.
So can these parameters, so for instance, if you have a distance decay parameter, you like it not to be growing with distance. Right. And if you take a normal distribution, how do you ensure that you don't end up with non-physical things?
Can you say that again?
It's the minute. So this is the same question: is how do you avoid non-physical models coming out of this sampling of a normal distribution, because the tail may go so far to give you the slope going the wrong way, for example, right?
Yes.
So the thing is, so what I need to do is constrain parameters to be positive by taking the squared or taking an exponential distribution, put that one into the functional form, take minus exponential the parameter. Then you run into the problems of the normality of the coefficient distribution. But I think there's a way around this.
So let's right. Christine, you've been holding. Go ahead.
I tried earlier, but okay. So going back, maybe it's too far ahead, but you were thinking of taking different combinations of GMPs to see if it could inform the correlation structure. But it seems to me that if you use a linear combination of these GMPs, you don't really add to the correlation information. It's already contained there. It kind of feeds into itself. So
no, but sure. I mean, if you take a linear combination of two GMPEs, it will have a different magnitude scaling than both the individual GMPEs, unless the both have the same magnitude scaling.
Oh, yeah.
Right? And therefore, you will get a new coefficient for the magnitude scaling.
So the difference, Christine, he's doing a linear combination of the ground motion.
Yes, the ground
motion. And we're doing the correlation structure of the coefficients, right?
Yeah,
so it's a little bit different.
Thank you.
Let you move on, and then we'll interrupt you. Okay.
So we are already behind time, I think. All right. All right. So this is just I'm just going through this for the strike slip case. It will be different for all the different cases. So I'm going through the strike slip case for Diablo Canyon. So near source strike slip near side strike slip sources. But for the normal case, the parameter settings will be different. The models will potentially be different. But this is just the example for the strike slip. So there are 7 GMPEs, the 5 NGA models, plus the Zhao and Lu model from 2011, which is basically the Zhao et al. 2006 model with the constant magnitude scaling above 7. What Bob pointed out.
Is it an example or real? I mean, you want to use it and the hazard at the end?
This is real.
Okay.
So
the question is that why you're including Zhao, that I really don't understand the magnitude saturation at first period of 5 seconds.
Right. So you have Zhao's model in there as a credible model that will define part of the space. We may, in the end, come back and chop that part of the space out. The other part I think we didn't cover is the Grazer and Calcom model. We didn't put here because it can't be captured by this common form. It really needs a different slope. It's got an increase with distance and then coming back down that we're not accommodating. And Nico will get to how we bring that one in at the end.
Right. So what I basically did is I evaluated each GMPE at magnitudes from 5 to 8. In 0.25 magnitude units, the magnitudes from the Joyner-Boer distance from 1 to 70 kilometers. There are 3 values of depth to the top of the rupture for each magnitude, just to capture the depth scaling for those models which have depth scaling. It's a vertical strike slip force, so it's easy to calculate a rupture distance from Joyner-Boer distance. The 30 is always 760 meters per second. The Z10 and Z25 values are calculated from these 30. And I evaluate each model for 5 periods. It's basically 0.01 seconds, 0.2 seconds, 0.5 seconds, 1 second, and 2 seconds. And then, so basically I get, actually I don't remember how many points, but a lot of ground motion predictions for each GMPE, and then I fit those ground motion predictions to a common functional form. And this would be the case for the normal case. so near source normal. Here, the GMPEs would be different. So basically, the EDRIS model gets out because it doesn't have a normal faulting term in there. Same for the Zhao model. But there are the two European models, the Acker et al. And the Bindi et al. So the ASB and the Bindi model come in. And since there are, the site will be on both sides of the fault, I'll go from Rx minus 70 to Rx 70. So this is like the basic idea, generate ground motions at these points, and then again fit the common functional form. It doesn't have to be the same one though. So you can use a different functional form for each case. But it just needs to be consistent across the case. I'm not going to show this. I'm just going to focus on the strike slip events that I think this will be enough. So this is the functional form as it is right now. So there's a linear depth term. There's the depth term with depth to the top of the rupture. And then we have the 3 linear magnitude scaling with breakpoints at 5.5 and 6.5. And we also added a, this should be MW here, same there. So we have a magnitude square term in there to avoid like a really sharp kink at the breakpoint.
Nico, did I miss? You didn't talk about reverse faulting, or you did?
I didn't. This will just, the approach will be the same. It will just have different depths. It will have different distance.
You get to
and
complexity of the hanging wall and so on. I don't know. Okay.
Well, the basic idea right now is that all reverse. So for the reverse case, we're always on top of the hanging wall. So you don't need to worry about some like distance tapering. So you can just take some linear term for the hanging wall.
Essentially, use of the hanging wall, we're going to adopt the a thing called scaling, but each GMP is going to affect the amplitude of the hanging wall term. What Nico is saying is our site is always over the rupture or very close to it, so we don't have all of the other complexities.
So what will happen to BSSA?
How does BSSA get used?
For the reverse case on top of hanging.
Well, they have an implicit hanging wall term by using
yeah, exactly.
So you will, I mean, they have that implicitly in there, so it will be captured.
It gets reparameterized, in this case, as a rupture distance model. And you could say, have you lost something fundamental? The answer is no. But you need to be shown that, right? No, in our application. Right? So now here's our question. It's not, in general, does this work for every case? The parameterization for this application, if we recover the hazard, then that's adequate.
I think really this is the key point, rather than generalize it for and so on. For this application, these two sites, that's the way.
Right. If you have distant reverse faulting events, then you need to worry about all this complexity of the hanging wall term. And then you have to use a different common functional form or go back to the original GMPE. That's right. And so basically, this is what we need to be aware of. Basically, these the linear distance term. So if we fit it, it will be negative. But if we sample from that, if we sample into the tails, it can be positive. So this is something we need to I need to address. And the same thing with the A4 term. In this case, if it's negative, but we can have a, so in this case it would be positive, but if we sample into the tails, it could be negative, and then we would actually blow up. So I think, so this needs to be addressed in a or as an exponential term. But then we get into kind of small, slight problems with the covariance matrix between the different GMPs.
Is there a fundamental problem if we just put a boundary and say, here's the minimum value for each of these, and if you sample it, we reject that sample?
I'm worried because of the correlation between, if this is very strongly correlated with some other parameter, that we're like throwing away contributions from other parameters that might be relevant for the other parameters. All right. So now I'm going through all of these 7 GMPs and showing you the residuals. These are the standard deviations of the fit, of the residuals of the fit. And as you can see, they're generally pretty small. The only one that has slightly larger standard deviations is the BSSA model. And that just comes from the point that this is a Joyner-Bourg distance model, and we're reparameterizing it in terms of rupture distance. So we're not capturing that everything that the Joyner-Bourg distance, the BSSA model has. Okay, so these are the residuals of the ASK model with respect to magnitude, distance, depth to top of the rupture, and this is just the residual distribution. And as you can see, so the residuals are fairly small. They're not zero because it's just a different functional form, but they are fairly small. So basically, I think this model has like a breakpoint at 6.75 and at magnitude 5. We don't care about everything below magnitude 5, but this is what we're picking up here.
Before you go on, what he's pointing out, you see in the magnitude scale in the upper left, there's a jump at 6.5. And you say, why is there that jump? Because I had a break in my scaling at 6.7 or 6.75. He's modeling it by a common form with always a break at 6.5. So when you go just on other sides of these sharp corners, you're going to get a misfit. And that's going to show up on these plots as we go forward. Okay, so we're essentially going to be smoothing through all that. Right. The hazard really doesn't care that much because you'll be a little bit higher for your 6.7, for example, or a little bit lower for your 6.5, and they'll be trading off. Why don't we smooth? Because he's trying to find a.
I mean, you need to find something, especially with the magnitude breakpoints, that is representative for everything. And for example, we're not capturing the Zhao and Liu model, which has a sharp breakpoint at 7.0. So we're just not capturing this flat magnitude scaling above magnitude 7, or actually 7.1 in this case.
Nico, for hypercentral depth, you use the correlation between Z-Tor. Okay.
So it's, as you had that in your paper, it's based on the Z-Tor and fault width. And fault width is based on magnitude in this case. So this is the residuals for 0.01 second, 0.2 seconds. It's still fairly small.
Try to stay close to the mic.
Okay, sorry. So I'm just going through the 5, for each model, I'm just going through the 5 periods. It really doesn't really change that much for the ASK 14 model. So this is for 0.2 seconds, so 0.5 seconds, 1 second, and then 2 seconds. And this is then the BSSA model. And you can see for small magnitudes, we get some small, fairly large residuals. And the reason is that for small magnitudes, we have a Z-Tor value of 7. And, well, actually, we have 3 Z-Tor values, and they will just generate the same Yes, they will just generate the same ground motion at joiner Boer distance of 1 kilometer, but the rupture distances will all be different. So we're capturing this geometric effect in this case for the small magnitudes. For large magnitudes, it doesn't matter because in that case, the depth to top of the rupture is 0. It's set to 0 or very small values. So therefore, we don't see that effect there anymore. This is the same thing for 0.2.
So before you go on, Yusuf, this is what you were trying to get at. You're saying this is what you're seeing is that big range is now missing. We're going to accommodate it by moving this model, or how should I say it? The values here are maybe plus or minus 0.2 or 0.3, and we're looking for biases. So you can see in close, there's a systematic misfit, right? Because of the way the GMP is going to scale, and that's a consequence of doing it. One alternative approach we hadn't talked about, but you could do all of these models parametered in RREP, all of the models parametered in RJB, and do it twice. And that may be the way to try to track it. You don't want to do it too many times or you'll never get done. Yeah, but that might be a way to deal with that issue. Because I think that's the biggest problem, right?
I mean, the same thing. So I did the same thing using joiner Boer distance as the distance metric. Then you have really, really small residuals for the BSSA model, but then the residuals for all the other models go up. Correct. So this is 0.5 seconds, 1 second, and 2 seconds. Campbell and Posognia works fairly well, especially for large magnitudes. For small magnitudes, we still have this. I think this comes from the different depths. Small magnitudes, we have like the main contribution of the depth term, the Vitor value, and since this is based on Vitor, and the model is based on hypocentral depth, we're actually having some slight misfit there.
We are breaking it also at 6.75. So how come?
So you're breaking, I think, at 6.5.
6.5.
Yeah.
Oh, sorry.
I think you're actually breaking at 5.5 and 6.5. Yeah. So at first I didn't have the quadratic magnitude scaling in there, and then it's like really close to your functional form, and then this is really, really small, the residual. Again, next period, 0.5 seconds, 1 second, and 2 seconds. But generally, the value...
One interruption. The scales are changing, right, on his y-axis. So you need to pay attention to that. These are all really small numbers, even though the points go all the way to the end, compared to the BSSA, where those are up to 0.3 or something like that.
Actually, like the largest ones for the BSSA are 0.6 for magnitude 5 and depth to top of rupture of 10 kilometers. Cho and Young behaves similar to the other rupture distance NGA model.
One question, Nico.
Yeah.
Is it possible to, even though these residuals are purely lack of fit, is it possible to account for them in the end, as, or are there issues of correlation that you can, so that we can say that they were not ignored? If they can be put in an epsilon term at the end, as we would do normally in a GMP, even though they are different because they are lack of fit. Is there a way to do that, or does it create problems?
Do you basically mean introducing a sort of error term?
Error term, but it has to be a random process, so, because it's not heavily correlated. So I didn't say anything.
I think the problem if you do that And if you then sample from that, if you sample from the function and then sample again from this error term, it will actually mess up because the error term will sometimes be positive, sometimes be negative.
It's heavily correlated. So, no, never mind.
I mean, the error term is, of course, also for each model heavily correlated with RGB. Should be dependent on RGB magnitude and distance. So I don't think you can. I mean, you can fit each model with that, but I don't think you can actually then generate new models for that.
Yeah, I agree.
Okay, we have in the past when we've done this kind of an approach, we've thrown in a sigma fitting and just shoved it into the aleatory term, and just bumped it up to make sure you're covering it.
Maybe that's the only thing you can do. Okay. But that would imply that numbers like 0.1 don't matter.
Correct.
And you can ignore them.
Right. So most of these are small enough, but the ones like in this particular case, the SSA models would be big enough we need to bring it along.
That doesn't matter, but none of these will.
We should emphasize that the example he's going through is for one particular case, which is the strike slip model for Diablo.
Right.
And the process, but with different inputs, will be repeated for the other ground motion cases. So, for instance, for Palo Verde, where strike slip at 200 kilometers is important, we would have to do the evaluation and the development and evaluation for that set, not based on these results.
Right. So basically, I mean, here the underlying data is magnitudes 5 to 8 and distances 1 to 70 kilometers. And then for Palo Verde, it would be distances much larger than that. Probably not from 1 to 100, but maybe from 100 to 400 kilometers. And then you would fit your new functional form to that one. Idris model has a breakpoint also, I think, at 6.75. That's again why we have this jump there, but otherwise it performs fairly well.
I think what Gabe said is important to keep in mind. Numbers around 0.1 or smaller are not very important to us. That's in the noise level. Above 0.2, we start to matter and have to keep track of it.
So this is now the Zhao and Gu model. So this is the model which has constant scaling rough 7.1. But it still fits. It fits worse than the NGA model, but on average, it still fits fairly well.
Well, then the strange magnitude saturation that they have here, how does it show? It doesn't show here. So magnitude 7.9, for example, you have. I assume that their model is going to be very different than, say, NGA at magnitude 7.5 or 8.
Yeah.
But you said this isn't comparing to NGA.
This is compared to the fitted model.
No. But if you your standard deviation is a small with Campbell and Buzorgnian, your standard deviation is also very small with Zhao at large this magnitude and long period. Doesn't make sense for me.
Their model, this is not comparing with data. This is comparing his ability to fit their functional form. That's what this plot is. So it's only he's got a magnitude break in his slope so his functional form, which is breaking at 6.5,
exactly,
with a quadratic term, is able to reproduce the Zhao and Liu model to this tolerance. That's all that plot is showing. It's not comparing against the difference between his Zhao and Liu and someone else's model, or between data. It's just the ability of this functional form to represent the Zhao and Liu results.
But the vertical axis is vertical axis, right? What I'm saying is that at 7.92 seconds, Campbell and Buzorgia, the range of the residuals that you see, if it's more or less the same as the same thing for Zhao.
Yes, that just means.
What is the meaning of that?
The meaning is that meaning is that he can reproduce both Campbell and Buzorgia and Zhao and Liu's ground motion models with this functional form to the same tolerance, with different coefficients, though.
Yes.
The coefficients will be different, but the tolerance is the same.
So this is residual of the predictions of the GMPE of Zhao and Liu to the new GMP, to the fitted GMP.
So this is slowly sinking in, and I think Bob, at least for me, made a good point there. Each one of these has a different set of coefficients.
Right.
So in a sense, I don't know how many you started with, 7 models or something like that. You're generating 7 new models, each with a specific set of coefficients that relates back to that original model.
So now we have, so the coefficient, so the functional form has 10 coefficients, A0 to A9, or A1 to A10 if you want. And now we have, for each coefficient, we have 7 values. We have 7 values for A0, 7 values for A1, each corresponding to 1 GMP. And then from those, this is the vector matrix, and then we can calculate the mean of the coefficient A0, the mean of the coefficient A1, and so on and so on. This gives something, I wouldn't really interpret that, but this gives something like a mean GMPE of those 7. And we have the covariance between the coefficients. And this gives us something about the spread of the GMPs. So, but not the spread in terms of aleatory variability, but the spread in terms of median predictions.
So let's stop. Is that making sense to people? Yes. So I'm seeing some heads nodding. Okay. But it's important that we get to this basic thing that he's trying to do here, because the rest of it builds upon that. So we now can have a way to compare the GMPEs and parameterize them in a common statistical way, right? Common framework.
There's a matrix now with 7 rows and 10 columns.
Exactly.
Okay.
Times how many periods? You're almost
Right.
there.
Times 5.
Right.
Times
Yeah,
times 5.
per period.
Correct.
Right. Exactly. Times 5. Okay. Yes. They are, in this case, so I mean, I'm fitting a different set of coefficients for different periods, but in the end, when I calculate the covariance, I'm taking all periods at the same time. Right.
Ken, did you have a question? Or?
I could either bring it up to you guys separately, because it's not that, but yeah, I think it's the visualization here. I think people are having problems. If you had some plots in which you showed the original equation and the fitted equation together, not everyone's used to seeing residuals.
We're getting there. We're getting there right now.
Oh, you're actually going to, okay.
No, I'm not showing like the, you mean like, yes, I'm showing.
Well, you've got the residuals
Yes,
here, right? But if you actually showed a plot, because
Yes,
that's what most people can relate to.
No, that's true.
Yeah, I know it
But,
means
I mean, it's still important to see. I mean, if we had numbers here which go up to 0.5 or something, and would have significant, like significant mass over there, then it wouldn't.
No, I agree. These are essential, but
it's
just
important to check that it's actually fitting, and that we're not over-predicting, under-predicting, or anything else. Or that we just
The reason I said this and that I wasn't going to, it's a documentation issue. I mean, people are in the here and be able to ask questions. Someone now needs to be able to read the report and understand this. And this is where I think the additional plots would be very helpful.
So this is the last GMP, and again, it fits fairly well. The JAR model also doesn't have a depth limit. So this is, I think, why we're seeing some larger residuals over there.
Be sure to talk into the microphone.
Yes.
Tempting to turn your head, but then we can't hear you.
All right, so this is the plots Ken was asking, they come later. This is Nick calculated hazard sensitivities for two fitted GMPEs, so for the ASK model and the BSSA model. The ASK model is one example that fits fairly well. The BSSA model is the one example that doesn't fit very well, or has the largest extreme residual. And I can, yes. So basically, so what we have is this one is the ASK reverse base case. This one is, so the red line is the ASK strikes, the original GMPE strike slip case. And I think it's green, which is actually the same curve, or almost the same curve, is the fitted common functional form, the hazard from the fitted common functional form of the strike slip case. And here is the total, I think. So this is black, so this is actually red and green. They just almost, they coincide.
They're right on top of each other, Christine. Right. So in the middle, there's two. The red curve.
Yes. The blue is the sum of these.
So our hazard at
Not me.
Okay. Is a combination of reverse and strike slip. Right now, he's only parameterizing the strike slip part, so the reverse is unaffected. So he's just showing you where the reverse sits. Okay. And effectively, there's no difference between these. The curves are so close that we can't tell the difference. So in hazard space, the parameterization made no effect. So if you said, what did we lose? In this case, nothing, right, in the aleatory term.
Okay, this is the same thing for 0.2 seconds. And again, we're seeing almost no difference between the base ASK model, or the original ASK model, and the fitted ASK model. In, Nick?
What the standard deviation was used?
So the public version.
Okay.
Oh, sorry.
All right.
Bottom line is there's no difference. So this reparameterization still reproduces the hazard for this model. Okay?
Yes. This is reassuring, actually. So this is for 1 hertz. And in this case, for low exceedance rates, there are actually some small differences. But
if you squint, I think you were staring, Christine, right at the bottom. You can see now a green and a red, barely, right? So effectively, they're the same. That's really what the answer.
And same thing for 2 seconds. And again, they're still very, very similar. This is the same plot, again, thanks to Nick, for BSSA, for the BSSA model. Same colors. And you see, again, that they're really, really close together. Same thing for 5 hertz. And here we see some differences popping up again at really low exceedance rates. And again, if you look closely, you can see some differences. You can actually even see them here between the red and the green curve. But so the bottom line is we can not completely reproduce the hazard, but we're like the hazard generated from the common functional form for both of these GMPEs and for the original functional form is very, very similar.
For this specific site?
For this specific scenario, that's right. I wouldn't use this common, if you had sites up to 100 or 200 kilometers, I wouldn't use this specific set of parameters.
Nico, all those plots go to what center? -6 at the bottom, is it? I can't see. 0, okay.
Yes.
It looks like 7.
Okay, so the changes was really below 10 minus 5,
5,
right?
6, 7.
Yeah, okay, thanks.
But we need to go that far in the hazard. We have to get to at least 10 to the -6 and down to 10 to the -7. One thing before, I think, Corolla, we should let people log in. If anyone has their computers, then you may be able to see it easier on your own screen. Do we have it? Are you running out of spots? Because there's 12 spots for those of you who'd like to see it on your screen. Yeah, we can see okay from here.
All right, so this is now broadening the model space. So this is the correlation structure of the coefficients. So basically, we have for each coefficient and each period, there are 7 values corresponding for each GMPE. And then we can calculate the mean and covariance for each coefficient. So what this is shown here, so this would be corresponds to the correlation. So this is the plot of the correlation matrix. This corresponds to 0.01 seconds, 0.2 seconds, 0.5 seconds, 1 second, and 2 seconds. And each of these corresponds to the coefficient. So this is the correlation between coefficient A0 and A1, both at 0.01 seconds. This is the correlation between coefficient A0 and A1. So A0 at 0.01 seconds and A1 at 0.2 seconds. And so on and so on. You can go through all of those. So, oh, right. Right. I'm really sorry. So again, this. Oops. So here we have again the correlation between coefficient A0 and A1, both at PGA. And here we would have the correlation between coefficient at A0 at PGA and A0 at 0.2 seconds.
So that's what you're talking about,
right.
Ralph. Does that make sense?
And now we have the mean of all of our coefficients, and we have the covariance, and then we can just sample from that. So we're sampling 1,000 new sets of coefficients. And from each of these sets of coefficients, we can make new ground motion predictions.
Gabe, you had a question?
Yeah, just one comment, just maybe to simplify things a little bit. The off-diagonal blocks don't really matter, right? Because we do PSHA one frequency at a time. The off-diagonal blocks don't really play a role, right?
But we are planning to weight our models independent of period right now.
Okay.
If we do that, we want to be sure we're creating the model at all. We want the spectral shapes to come out okay. So if you don't have this, you'll lose track of the spectral shape.
Right.
All right. Yeah, if you're weighting, if you're assigning weights model by model at all frequencies,
That's
you need the whole thing.
Right.
Okay.
So this is also, I mean, 5 periods is not enough. I mean, and in the end, it's probably better to do it at more frequencies. But otherwise, you can still do that. So you have, in this case, you have the correlation also between periods and periods. So that
we also want a kappa adjustment, and we need the kappas to come out proper, right? So we got to have the correlation. I think Nico's right. Well, this will be run for maybe 20 periods at the final thing, so we have it all, but the structure is still the same.
Okay, so this is now, again, everything in 1 or 2 plots. So what we're doing is, at first, we're generating for the 7 GMPEs, we're generating data at particular magnitude, distance, and frequency values. And then we're fitting each of those to a new functional form. So in this case, the red lines are the original GMPEs, and the blue lines are the fitted GMPEs. For that particular scenario. So for that particular scenario, it works well. I'll show you some later where you see larger differences between the fitted models and the non-fitted models. 7 is here.
Magnitude?
The
right hand side?
No, this is 6.5.
Okay, that's
And then we're generating 1,000 new models from the generated mean and covariance of the coefficients. And that's how they look like. I think this is the same plot that Doug already showed, without the blue line. And what we see here, so we see that we have some edge models over there and also over there that don't behave physically, and this is just because the coefficient space is unbounded in this case. Most of this is taken care of by the correlation, but we're still sampling a little bit into the tails, and therefore we get some coefficients that are just non-physical. So in the end, we need to restrict those. So we need to make some restrictions on the coefficient. And then, what we then need to do, we need to evaluate these new models. And so here I plotted a green line. The green line would be the model of Greiser and Kalka. So this is just one way to look at it and say, do we capture that? And where does it look? Where does it lie in all of these, in the whole distribution of our new model?
Or if you included a curve in the beginning, then what would be the difference?
Right. But I mean, so the reason is, the reason why this is why this was excluded is because it has this slight bump here. It has a bump at short distance, which is not which we don't capture, and all of the other 7 models don't have that. So this is why it's not in there.
One suggestion, Nico, purely as a presentation thing, it might be useful to take a few slices and a few magnitudes and plot the distribution.
Like this?
And that way, like that. That way you'll see. That way you'll see that again, because the range is a little scary. And in fact, the mass, the mass is down there in the range where it should be.
So this is one. So this is, for example, where
Nico, talking to the mic.
Oh, sorry, I'm really sorry. So this is now close to the source. So this is Joyner-Boer distance of 1 kilometer, and on the right, this is again magnitude 6.5, but this is for 1 second. And what we see here is, for example, so this is the Boer model. So we're not really capturing the Boer model at that point, which is due to Joyner-Boer distance. Oh, I'm sorry. So this is the BSSA model, which is in Joyner-Boer distance. And this is also for 1 kilometer, Joyner-Boer of 1 kilometer. We have the largest largest residual. And this is what we see here. And the question is, what are we going to do with that? Does it matter? That, I mean, we are, it's still captured within the 1,000 models.
Well, yeah, of course, but I think you have to, as Norm said, that's at least one way of thinking. Redo with RGB and then you see what you get. Your generic or general functional form, assume it's RGB. Redo it, so rather than
we just do it twice.
Yeah, exactly.
Right. But what are you going to do then? Run the hazard like 20 times?
Yeah, that's what he's
exactly
saying. So every time this hurts our hazard people here because we've just doubled the amount of runs. But that, if it's an important parameter, we need to do that.
So Nico, looking at this, at least the NGA models also have epistemic uncertainty models associated with them. I would expect this to be a broader distribution than that. So maybe you're not the appropriate person to ask. I'm aiming it at the TI team here.
Right.
But have you looked at that and ensured yourself that this is capturing additional uncertainty? I think you'd expect it to be more than just the epistemic uncertainty on individual models.
Well, we need to, right now he has not put that into his simulation process, but we need to put that into the epistemic uncertainty on the individual models needs to go into worked into the simulation of the parameter space.
Oh, okay. So you're,
but as a part of new models, yes.
So this isn't meant to be an alternative to that.
No, that would be captured as a part of generating new models. Is how certain are the models that we're starting from?
Okay. The thing is, so the way it is right now, using the peer report of Linda and Bob, which just gives you a number. So basically, the only thing I can do with that is scale it up and down. But this will only affect the T0 coefficient.
I mean, but there is a magnitude scaling on it, that term, so it would change the coefficient at magnitudes above 7.
Right. But I mean, in general, you should have uncertainty in your magnitude scaling.
Right.
And this will not be captured. And
I think it would introduce some magnitude scaling uncertainty,
yes, because, for example, distance scaling uncertainty will not be captured.
No, but it would be just an added component to this possible expansion of the space. We don't know whether it would expand it very much or not, but we haven't tried it yet.
Even in this way you put it, Nico, wouldn't it increase your C0 variance?
It would increase the T0, but it would not affect the coefficients related to distance scaling.
Sure. So you would have, though, a broader set of ground motion models at the end. Part of what Ken said is this needs to be at least as big, and it should be bigger than the epistemic uncertainty we already associate with the models just due to their
Okay, let me go to this plot. So this is a slice through here at 6.5. I should make this plot for some other ones, but basically this is, so the histogram is the distribution of the 1,000 ground motion predictions at magnitude 6.5 and Joyner-Boer distance of 15 kilometers. And these two normal distributions are the ones, they have the sigma of the NGA uncertainty model, and they are centered, in this case, on the largest GMP and on the smallest GMP. So this would be, I'm not exactly sure whether this is actually an NGA model, I don't think it is, but this would be the uncertainty associated with the largest GMPE, with the GMPE that gives the largest prediction at this point.
That's probably Zhao, right? Or would be the,
yeah.
So when Nico first showed this, and we had a discussion a little earlier, my first reaction was, okay, we captured it, right? We're bigger than that range, we're okay.
Well, the thing is, we're not,
but not right on the edges.
Not
yeah,
right,
not down there. So that was at 6.5?
That's at 6.5,
okay.
15 kilometers.
So if we took a different slice, so Gabe
Right.
show me a few slices, we may see a range where we're not broad enough. But if we did what Bob said, you would broaden the C, at least broaden the C0.
You would broaden the C0.
Yeah, exactly.
But you're only broadening the C0.
Primarily, I think what he said.
Yeah, okay.
It's not just a constant, it's a magnitude.
The constant magnitude. Oh, so
It would broaden the estimates above magnitude
Yeah,
7 because the epistemic uncertainty model expands above
Right.
7. But below 7 is just going to broaden C1.
Then Nico,
C0. It's actually area 0.
C0.
Nico, Linda and Bob had it only for NGS. You have a couple of others. Then if you broaden C0, then how does it work? They have the variation
Right, so
of...
this is the variation of the NGA models, but
Yes,
I don't have the information for the JAR models. We can probably get them, but this would broaden the range of C0, and I think it will be captured if we include this beforehand.
Yusuf, we would take this and say, look, we have models with, we think are the largest data sets. These are the best constrained models. This is as small as it can possibly get. When we go to bring in the European models or Zhao's model, that's already now shoving that median to another place. And I don't need to then add on to the uncertainty on that in addition. So I think we're okay just with what's available.
Nico?
Yes.
Sorry, I want to just check and make sure I'm still following on a conceptual level. Could you go back one slide? Okay. So you were talking about the BSSA, say for the low magnitude.
Yes.
It's kind of at the edge there. And that's a result of this different parameterization for distance. Is that generally the same if, for example, you didn't use that, but you used Brazier and Kalkin? Am I thinking of that in the same way?
I'm not sure what you mean, but I
You're
mean,
saying, what if we left that one out?
Yeah.
if we left that one out,
And then just plotted it at the end, comparing it.
Yeah, to me, and I want to make sure that I'm
Yeah,
thinking
sure,
of this
right.
correctly, is that conceptually what you're doing
Yes.
with Brazier and Kalkin?
Yes.
You left it out.
and then I'm plotting it on top of it and see where is it in the range
Right.
or not.
And by that same token, if you had included Brazier and Kalkin, it might end up being, you might find a parameter.
I mean, then of course you will have some slightly different mean parameter distribution and some slightly mean covariance, but I don't think it will be that much different. So basically the new models that you will create, if you include the Brazier and Kalkin model, will be similar to the ones that are created here.
Thanks.
I did the same thing using only the 5 NGA models and leaving out the JAR models, and the range of ground motions I get are almost the same as if I include them. I think it's really difficult to look at all of this because we're having different magnitude scalings between the models. We're having different distance scalings between the models. So even if the range is the same, still the Brazier and Kalkin still has this bump. So even though each individual prediction is covered, the whole range, the whole functional form is not. And this is, I mean, it falls inside the range, and it will also look later on the map. It will just fall inside, but it's still fundamentally different. But it's difficult to pick that up automatically.
But I think we could also argue using RJB or RRUP is fundamentally different, and that's what Youssef keeps telling us, right? So there are some simplifications we're doing. In the end, we want to be sure that we don't have every model captured, but we get the range of the hazard, right? That's our level of success or failure. Did we get the hazard captured right?
This is right. I mean, even, okay, I've forgotten the numbers, but if you say, okay, I don't care about this, I don't care about magnitude 5.5 because in the aggregation they're coming at really low probabilities, then you can say, okay, I don't really care whether I capture this or not. Then you will still capture the range of the hazard. And
Nico, how many are these here? 1,000?
1,000. No, actually, it's 1,008 because it's 1,000 new sampled model plus the mean model plus the 7 parameterized GMPs.
So if you reduce it drastically, what is it? Instead of 1,000, 20. What is? How would it be different? And I have a reason to ask. I'll tell you later. What would be different if instead of 1,000 you go to 500 and then or to 20?
I just
Joseph, are you asking the question of the sampling or the result? The result is that we have 1,000 models. We have to come up with a representation of that distribution by 10 models, which would capture the same effect as running 1,000. We're not there yet. If he just ran 10 models, he would not get. He would just get 10 lines. But he's going to run 1,000 models, and then we have to represent that space by a small number that is amenable for hazard calculation. I think if Robin was here, that's like 500 or something like that. So the rest of us only use 20.
I guess I'm still a little confused. I mean, we're trying to understand what's going to happen, say, in 100,000 years or something like that. And if we were taking, say, a Bayesian approach to this problem, we could say, have one person come up with a set of Bayesian priors and say, I think the answer is 1G at this site is my Bayesian prior. Yeah. And the other guy could say, I think it's a quarter of a G. And then you go into the regression and see, does the data force you to the quarter G or does it force you to the 1G answer? And it might be that the data is insufficient to force you away from your prior distribution.
Yes.
And if that's the answer, that your answer completely depends on your prior, then basically we don't know, in as much as you don't trust one person more than the other, with one person's prior other than the other. This approach that we're talking about here, it couldn't tell us any more than that other Bayesian approach could. I mean, it just says here's kind of a range of.
This is true, but in the end, I actually thought about this. I'm not there yet, but I'm showing you comparisons with data. But I'm also showing you the likelihood that the data is generated by each model. And then you could actually combine this. So you could say this is the prior of my model distribution, and then you update this with the likelihood that it gives you the data.
So the prior, usually when we do these things, is based on some physical intuition that we have, some principle that we're going to use. We say the data may not be sufficient to take me to some answer, but based on some physical principles, I'm going to prefer a certain answer over another one, and I'll only diverge from that when the data requires it. But of course, that's just telling you, if you don't know the physics and the data doesn't tell you, you just don't know the answer, right? I mean, so you could start with, so this is trying to find the whole range of things as opposed to...
This is trying to find the whole range, and then in the end we need to reduce it.
So we need some prior then to reduce it, right?
But our prior is the GMPEs, which had just what you said. We did. Don't think of them as empirical fits to data. They are much more than that. There is a whole lot of constraints. That is how we think the physics behind how ground motion scales is built into it. And we'll build things and we'll say, you know, the data don't quite fit it, but I'm going to stick with my model until I get enough data that forces me off of it, just like you're saying. That's the way the GMPs are developed. And you'll see, you know, good issue with oversaturation at high magnitude. The data keeps going down. We don't let it do it. We say, I'm going to stick with that, and another 10 years we may get pushed to that level, but we haven't had enough to push us off of our prior. But those, so there is a lot behind those GMPEs, behind just here's a form, let me see what the, you know, run a regression, here's the coefficients, and I don't do anything with it.
I mean,
a whole lot attached to those.
I mean, you're right. The better approach would be to enforce all of these assumptions that go into the GMPEs in terms of a prior distribution. That would be, I think, that's a more principled approach, and it gives you a nice probabilistic interpretation of everything. But in the end, prior elicitation, especially on coefficients for the GMPEs and the complicated functional forms that you have, is different. It is difficult. I'm not saying that it can't be done, but it's just difficult. And in the end, so now that the GMPEs are there, we need a prior over the GMPEs. And this is, again, very, very difficult to come by. But you're right that the Bayesian approach is always better.
A true Bayesian is up there.
I have a question. So now when you do this, you capture the range, and then you come up with a subset of models that follow that. But as you mentioned, these models won't capture bumps or specific shapes. Is that a problem, or you only care about the range, and you don't care about correlation of a hazard with distance or with periods?
It is a problem if it matters in hazard space. That's not a problem if it doesn't.
Correct answer. That's where we
Exactly. I think the key is that for this specific site, it works. For another site that you are saying the bump is important, you have to do something.
Yes.
And then, Nico, I have a very different question. So basically, you can generate 1,000 or 500 spectrum, right?
Yes.
So that can be used for ground motion selection, time history selection for analysis also. Then you go to the large database, each of them. You find one.
I mean, each of these is a median model.
Right.
As a median prediction.
Right.
So
then if you go to the huge time history, time series database and find the one that is closer to each individual one, you are going to have 500 time series, right? I think it has another application for structure analysis.
Okay.
But then how do you consider epsilon? It's all for epsilon 0, right?
Christine, can you talk a little louder or closer? I can't quite hear you.
You can't hear me?
No, I know.
Wow. Okay. But following what Youssef was saying, because these are all median models, that would only apply for selection based on epsilon is 0, right? If you want to select another epsilon, you need to incorporate this variability that you don't have here. These are median, right?
Yeah.
Okay.
I'm completely lost. Could you?
What?
These are median models. So I'm not understanding what
So
you're getting
you just thought about a clever other way of using these results and use them for time series selection, and you could pick those and then pick the time series that comes from this model. Yeah, it's future.
Okay.
Yes, we're trying to find further
It's not
applications.
part of this project.
Exactly, out of scope.
All right, so now we're coming to the part that we need to evaluate those 1,000 models. We have 1,000 models, and the question is, what are we going to do with them? And to do that, I'm going to visualize them in 2D. So if you remember from the last workshop how that works, we're actually treating each GMPE, and this means each of these 1,000 models, as a point in a high-dimensional space. And therefore, we're going to evaluate the each of these models add a grid of magnitude and distance values. And then this gives us a high-dimensional vector, and then we're just visualizing this vector in high dimensions in 2D. And the way we're doing this is that we're trying to preserve the Euclidean distance in high dimensions in 2 dimensions. So that points which are close in high dimensions are close in 2 dimensions. This is basically what we're trying to do. Example.
Quick question before we move on. You say you evaluate the GMPs for different settings of predictor variables. What kind of range are you talking about here?
So in this case, it's, I have that later, it's magnitudes 5 to 8 in 0.5 units and distances 1 to 30 kilometers. So it's basically 1 to 10 in 1 kilometer steps, then 15, 20, and 30 kilometers.
So the predictor variables are contained with your developing of the model when you started this.
Right.
Okay.
So they're inside the range, but they're also they're based, well, they're kind of based on the deaggregation. So that's the ones that matter.
So remember at workshop 2, I think it was, we talked, it might have been Gabe said, you know, weight the vector based on the aggregation. We're doing that in sort of a yes-no right now, but he's cutting out the larger distances, for example, so that we focus in the Salmon's maps, what are the differences in the models where they matter, right, to the hazard.
Yes. So basically, but in this case, we're still treating each point or each entry of the vector as equally important. So magnitude 5 at 1 kilometer is equally important as magnitude 6 at 1 kilometer, and so on and so on. All right. Just as a reminder, you've seen this picture before.
Quick clarification. Yeah. Ideally, you would use the height of the disaggregation participation.
Well, ideally, we actually would use this distance and hazard space, because that's what we care about.
Okay.
How different are the different GMPs in hazard space. To do that, you would need to run the hazard for each model. And so we need to find some shortcut. A shortcut would be weighting by deaggregation.
Yeah, exactly. Okay. Thank you.
Okay. So this is just basically how it works. Here we have 32 pictures of ducks.
Talk into the microphone again.
Okay. So we have 32 pictures of ducks. Each of them is 32, 1, 2, 3, 4, 5, 6. No, it's 18 pictures actually. But each of them is a 32 times 32 pixel image, and each pixel has 3 values, red, green, and blue. And so this gives me a total of a high-dimensional vector with about 3,000 entries. And then I can calculate just the Euclidean distance in these high dimensions in 3,072 dimensional space, and then try to recreate the distances in 2D. And this is how it looks like. I'm not really sure if you can see this, but basically this is where the models fall in the end on 2D, or where the different ducks fall in 2D. And what we have, I'll go back, is actually that they're aligning on a circle, or more or less on a circle, which goes like this. So basically, different ducks, or ducks that are similar we know that they're similar because we can just look at them, fall on similar points on the map. And now when you think of this, so this is just think of this as a grid of magnitude and distance values, and instead of 3 red, green, blue values, we have 5 period values. Put all of this into a high-dimensional vector, project this down. So fundamentally, there's nothing, or in terms to the algorithm of creating the visualization, there's nothing different between this picture and the GMPE. All right. So this is how it's done. So basically, there are 6 magnitude values, and these join the Bour distance values, and 5 periods. And this is what the map looks like. So here, what we have is each red point is the original GMPE. Each blue point is the fitted GMPE. So it's the new model. It's the model using the fitted common functional form for those GMPEs. And as you see, they're pretty close. And each of the gray points is one of the sampled models, one of the 1,000 new models. And then we have here, we have the Greiser and Kalkan model, which is inside the range of these 1,000 models. They need to use this one. So the Greiser and Kalkan would be there. And the black dot is the prediction using the mean parameter vector, the mean coefficient. It's also important, I mean, this is based on average distance in ground motions. So therefore, we're not kept, if something has a really weird shape, it could have some wiggly shape, but still have an average distance to one of the models that it's just close. And then it will still be close to that model on 2D. That's just something we need to keep in mind.
Nico, could you do me a favor? I don't know if I'm the only one who cannot see, but can you do with an outline of the contour or where the GMP points are? Because I don't see. I see a couple blue points, but I don't see.
So here, so this is the Idris model. This is the Zhao et al. 2006 model. That's the Zhao and Liu model, ASK 13, BSSA, Zhao and Young's, and Campbell and Bosonia. And this is the whole space of the GMP. 1,000. And now I'm going to show you a lot of contour plots. This is what we're trying to estimate. So this is, the contours are Euclidean distance and high dimensions. So this is why they're kind of circular. They're not completely circular because high dimensional space is not 2D space. So we're losing something. We can't reproduce everything that was there in high dimensions in 2D.
But Nico, this is the distance to the center model, correct?
Yes, right. So this is distance to the center model. Right.
So if everything worked out ideally, these would be perfect contours about the center.
Yes.
But
it's because we can't reproduce, I mean, they're just not falling on a two-dimensional manifold in this high-dimensional space. It's ultimately the ground, these 1,000 models are some sort of cloud in high dimensions.
So before we go to the next step, and we're going to run over, and I'm not surprised on this, is this making sense at this point, what this plot is? Some yeses, some no's. Ralph, go ahead.
But I still don't have a good feel for, let's say, what a dimension of 5 is on coordinate 1 or a dimension of 5 on coordinate 2. In other words,
it doesn't have a meaning.
It doesn't have meaning.
That's not no.
Okay.
We're going to get to help you in a little bit as to what to do by putting something on the background that shows you, for example, the mean bias in the models versus the data. And that will help give you a physical understanding. So we're going to get there.
Yeah, because right now we have no idea whether or not, in other words, if we don't know what those units are, then we have no idea whether or not they're really close. They look close on the map, but we don't know whether or not they really are close.
Right. That's actually good. Yeah.
That is twice as high.
Yeah. I'm glad I came, Yusuf. Thanks. Actually, so one part that I'm unsure about, if you go back one slide, I'm not sure how you actually get the points to plot here. You're collapsing the multidimensional space down to 2D.
Right.
And is that just beyond the scope of what you can explain at this point?
I mean, there are a lot of different algorithms to do that. So this basically takes, basically as input, you take a random collection of 1,000 points. You look at the distances, and then you randomly shift them around until the distance distribution in 2D is close to the distance distribution in high dimensions.
I'm not sure if that helped. So are you actually, you have the models.
Right.
I guess what I'm missing here is, in order to do that mapping, are you actually sampling the models for a specific case?
Yes, right. So this basically, I'm having a grid of a magnitude distance grid. So basically magnitudes 5, 5.5, 6, to 8. Distances 1, 2, 3, up to 30 kilometers. For each of the 1,000 models and for each of those grid points, I calculate the prediction. And then I just put this grid, the predictions on the grid for each model in a long vector, in a high dimensional vector. And this is my high dimensional point. So this high dimensional space is the model space. And each GMPE now is the point in that space.
Right. Okay, I get you.
And then I can look at the distance between the different GMPEs in this high dimensional ground motion space. And then I'm reducing this back to 2D.
He's just taking the sum of the squares of the differences between each point in the vector, right?
Yeah.
Right.
Okay.
Tom?
So the center plot point looks to be more or less a centroid of the actual finite number of GMPEs that you didn't generate. Is that the case? I mean, so
you mean basically the center of those 7 red dots?
Yes.
I think that's actually pretty close to the green. It's not exactly at the black point, but it's pretty close to the black point. Green is here. That's the Greiser and Kalkan.
I guess how much does this plot depend on where the 7 GMPEs that you used in the first place? If I removed all of the GMPEs on the right-hand side,
then this will move over there.
Then this thing would move over there. So it's not actually telling us which clouds actually fit the data.
No. No. So we're actually coming. So basically, the idea now is we have this point, and then we want to have where do we center, and this is the question: do we center here? Do we center there? Do we center over there? So basically, where do we, in the end, center? This is the fundamental question that we need to ask ourselves.
And that's what we'll be talking about the next couple of days. Where do we center the model? Because he'll show data, and these aren't all centered on subsets of the data. Right. And that's not a surprise because the models aren't simple, non-parametric fits to the data. They have something else built into them.
So, but as scientists, I mean, part of our job is to ignore things, including people. And so you see a lot of models out there, and sometimes your job is to decide, well, I'm not going to listen to that model anymore. It just doesn't make any sense to me.
So, and we've done that. So this isn't all, we've been collapsing them down already. So, yeah, we've got 7 that are for this case. For the next case, like the normal faulting, we'll have a different set. But let's push on. We're going to run late, and I knew this would happen. So I'm going to tell you that, well, I may not like this. I'm going to say there is no break, but go up and grab yourself a cup of coffee or whatever. Just feel free to get up, and we'll keep pushing through this.
Okay.
This is really fundamental to the next couple days, or we won't get anywhere. All right, and we want to get feedback on what we're trying to do, and that you understand these things. Okay, so let's push on.
All right. So basically, this is the question that one needs to ask. So basically, what you could do is you could say, okay, Doug already showed this. I'm going to use something like this as my center, and then I want to capture this range of all the models, and so I'm just going to go around here. But the question is, should you center on the black point? Should you center somewhere else? Or should you use a circle? Should you use something else? This is, in the end, the job of the TI team. And
so we could pull that whole thing over and say, no, you know what, the data are to one side. I want to shift it more to where the data are. Or no, I believe the modelers, these 7, have captured the right way things scale, and I want to center on them. Or maybe it's not a symmetric distribution. I should skew it a little bit to one side. That's what we're going to be talking about for the next couple days in terms of how we can be going about that.
Okay, so basically,
it seems to me that also we should look at the range, the amount of variation within a given cell, and maybe that should be something that is equivalent among all the subregions. So in other words, the larger cells might have more differences in the GPEs that are contained in those.
So basically, if you go here, I mean, these cover a larger range, and also they're probably more different from here to there. And it's also, of course, if you do it like this, how do you come up with a representative model inside there? And this is a fundamental question, of course.
Okay, I have a question, and it's maybe very basic, but to me it's going to make more sense what we're trying to do here. When you plot the greater and CalCam there, you never parameterized it, right? So how did you do that?
I mean, I didn't characterize it in terms of functional, but I can evaluate it at the same grid point.
At the same grid point, and you still project?
Yes.
Okay, that's critical, I think, to understanding how these models.
I mean, I can generate like at the same grid points for different GMPs that were not used to capture that, and then I can
really
say
an advantage then.
Right. Hang on, and so we'll get to how you can bring in the simulations, how we can show data. I think we got to go a couple more. I've been encouraging that process. Let me stop you for a few plots, and I think it will start to pull together.
All right. So basically, to evaluate the model space, you have different information. One thing is, where do the GMPs plot? You can say, okay, there went a lot of effort into creating the GMPEs. So you don't want to center somewhere that's like really far from the GMP. Probably not, because that's still the best information available in terms of what you have. There's also data. I mean, I'll show that next. There's data from the NGA data set, or maybe from other data sets in the same range that we created our functional form. And then we can evaluate each new model against the data. And then we can see, okay, is it bias high, is it bias low, how does it look like? And we have simulations. So there are the simulations, and we can plot the simulations on the same map and see where do the simulations fall. And I'm going through that, through all of that in the next slide. So first is the comparison with data. So this is the data set underlying the Abramson et al. 2014 model for Joyner-Boer distances smaller than 70 kilometers, magnitudes greater than 5, at least 3 recordings per event, and VS30 values larger than 250 meters per second. And the data is corrected to 760 meters per second to VS30, because that's the VS30 value that was used to create all the models. And only strike slip cases. So then we have 27 earthquakes and 435 records. This is the distance distribution, magnitude distribution, and this is the magnitude distance distribution. Okay, so for each of the 1,000 models, or for each of the new models, I calculated the residuals to the data. I split them into between event and within event residuals. So then I have, for each of those 1,000 models, I have between event, within event residuals. I can calculate the log likelihood of the data given the parameters of the model. And then I'm going to put that one onto the map. I'll show you this next. And to do that, so this is all based on the Abramson and Young's 1992 paper, just random effects on the residuals. And for this one, I assumed a fixed tau and phi. In this case, I just used the one of the BSSA model. The results are not totally sensitive to that. All right. And then I'm going through this period by period because the residuals are different from period to period, and if you just do everything on one period, it's difficult to evaluate. So this is just the same thing as before. So this is magnitude distance grid just as at 0.01 seconds. All the models evaluated at this grid, projected down to 2D. And this is again the contour plot of the Euclidean distance to the mean model. And this is now a contour plot of the mean between event residual of each model. So so for each model, I have the between event residual, so that's 35 residuals for each earthquake. And then I calculate the mean of that. And then this is the contour plot of that. So the zero line is...
So before you go on, Ralph, this gives you something to hold on to now, because you can see the values of 0.1 or something. Is that what your step size there is? 0.2 is your contour. It's a 20% change in ground motion. So you can see as you're stepping about the width of a 20% change, and you can see as you go left to, north-south, or what is it? What's that direction? Northeast, southwest, left in that direction, you're going. Yes, you can see that those are parallel, and so you can see, all right, those are on average just a shift. And so this gives you something to see where the models are centered. Do you want to be centered on a 0 for this subset of the data or not? So that gives us a place to start our evaluation from.
Then, Nico, what about, I think this includes, the data includes, for example, aftershocks, because
yes.
So what about, how sensitive is this if you use main shock, for example, or TIT has it?
There's not very many aftershocks because it's a bigger event.
It's about 5.
But there are some, you're right. So we need to do this for different subsets.
Correct. So I've done, so this is all the data that's in the NGA West model. I've done the same thing just using the Californian data. It's not very different, but it's just the worldwide data is made up mainly of Californian data. There are some other ones in there, but it doesn't reduce the number of earthquakes and records by a large number. So, yes, Bob.
Yeah, I'm puzzled about with the 7 models. The stipulation seems to be that these are independent enough of each other that the fact that there are 7 and they're treated sort of equally is a valid approach to get to the point of departure. But here's what troubles me. Let's suppose there were 14 models, but all 7 of the new models were really very similar to model number 1. Why? Because they're all students of model number 1. Or they all used the same physics. Or they had slight differences. Then you'd find that the mean was real close to model number 1, because you now have 8 models number 1, and the other ones are just 2, 0, 5, 6, 7. And
but don't focus, Bob, on the mean, because
no,
he's just showing that, but that's not where we're going to center.
I understand that.
then there would be an undue weight on that model compared to the others, because there are all these students of model number 1 that showed up that were given equal validity. And when you're trying to do this Euclidean distance, there would be a whole lot of real small Euclidean distances along with the other ones that you're showing. And I'm worried about that as a bias.
And I'm not, and so let me tell you why. The structure here, let's say I had 5 or 6 models all clumping them close to one of those.
Yeah.
In this space right now, they would be like that, but I don't give equal weight to the models. I'm going to map out a space in here. So they would all fall into the same zone, and I'd say I need just one of them to represent them, and it gets the weight, and the rest are tossed out. That would be one way that we would do.
Okay, yeah, but you would have to intervene to do that.
Not yet, because he has, remember he had the little grid on there,
Yeah,
the spider web?
Yes, I'm watching this.
So the spider web part is where we could say within all the models that fall into that one, they all get, we give a weight to that zone. We don't give a weight to the models within them.
And then the Euclidean distance from that zone to the others is what you would then see.
No, that was just a way for him to show you how smooth the model was. And,
right.
And
okay, thank you.
And the efficiency of going from high dimension to low dimension.
No, you clarified that. So when you're doing that, okay, right.
So the weighting is really important. So I think what Nico has said, where you center it, how you assign the weights, and are they symmetric or asymmetric is not his problem. Okay?
No, that's your problem.
Exactly. So we have to do that and explain to you why. He's setting up the structure that we can do this in an organized and systematic way.
And then if this is working correctly, you would account for the fact that I might have just called out by noticing that.
Yes, we would see them all clustered together, and that doesn't mean
that doesn't mean they're all individual. There's a zone there that are similar enough.
Right.
So if you, for example, if you have like 2 models which are the same, they would plot on the same thing. But if you just weigh them based on it's a good paper and everything, you would give them equal weight. But if they fall into the same zone,
Norm, that helps a lot.
Right.
Thanks.
Adrian.
How do you get around the fact that because you're computing mutual distances between all the models, if you add a different model, all the distances will shift. So your map will shift when you add a different model. So if you were to add, let's say, a crazy model, then all of a sudden all the others will cluster closer to each other because of this new crazy model. And when you're looking at zones within your map, all of a sudden these models may look like they are closer to each other.
I mean, if you have just 1 or 2 outlier models, and then it would just plot over there. But the other distances don't change in the high dimensions, They don't. I mean, we're trying the distance between this point and that, or between here and there, in the high dimensions doesn't change if I add another model.
No, but one related question. If you want a model that doesn't have to be an outlier, if you want a model that is reasonable, will the Summers map change substantially, or does it just perturb a little bit?
Can you say that again?
If you are one model which is more or less typical, will the Summers map change completely, or does it get perturbed a little bit?
The thing is, we have 1,000 models here, so 1,000 models already give me a good representation in 2D.
So when
if you only have like 6 or 7 GMPs, one additional model can actually change the map substantially.
Okay. If he drops in a new model, like simulations, if we can get there, you'll see the rest of them aren't jumping around.
Okay.
Okay. So because he's got 1,000, it's pretty robust.
Stable enough. Okay. Okay. The other question is, if you thought of this in a patient sense, isn't it true that we're using the data twice?
Yes, and so I wouldn't say these are not updating it at all.
Okay.
Right. Okay. I'm not. I mean, this is just still the only data that's available for this case, and of course, the 5 NGA models were based on that data, and so therefore, if we're now using it right, that's a problem. But that's okay.
But we're using it twice in a different way. This is a subset for this specific application. A lot of the models are borrowing strength from saying, what do I see in reverse? Well, I'm going to help that scale my strike slip because it all has to fit together. Now you see where those models fall. They're not all right on the 0 line, right? They're sitting at 0.2.
Okay, one last question for me to try to understand. Sound map. These sound map are somehow, they're rotationally invariant, right? You could have rotated it 45 degrees.
Yes.
And define your T1 and T2 differently. Okay, so I shouldn't bother me that the 0 bias line goes more or less diagonal.
No.
Purely accidental. No. Okay.
So these are sitting on 0. Is that correct? In this case, are close to the 0 line. Okay.
Okay.
I mean, I'm not showing this, but if you do this for the normal case, they're not sitting on the 0 line. And the reason is that, as Norm told me, that the developers just didn't do what the data wanted to do for the normal case.
Had a strong prior, and the data was, there's not enough normal data to push us off of it. That's really, let's try to get to the...
All right, so this is just the next thing. This is the contour plot of the mean within event residual. The numbers here are much smaller now because that's just the way the within event residuals should be centered at 0. Some of them are not exactly centered at 0, which I think is just due to that I used a fixed standard deviation. Yes, so that's 0.08 and minus 0.08. And here we had minus 0.6 and plus 0.6. And this is the contour of the likelihood. Oh, that's really bad to see the outline here, but so this is the likelihood of the data given the parameters, if you just think about this. This would be, if you're running random effects, you would optimize or maximize the likelihood, get your sets of parameters and your sigma out. But I fixed sigma or fixed phi and tau. I have my sets of parameters, so I can just calculate the likelihood. And then I can plot them here. And what we see is we have a fairly broad region of high likelihood. So there's a fairly flat region of high likelihood in the middle of the data.
Okay, so I need you now. So these are the basic plots. All right? You've got the points put on top of the mean event term. So you can see basically what the bias is in the model. He's got them versus the intra-event, which is not that informative, really. And then this is the likelihood that these data will be produced by each one of those 1,000 models. Okay? So those are the basic things that we're going to be going. Can you get to a simulation plot?
So I've got the same thing for the different simulations. Okay, I just come to the simulations. So for this case, I get from Katie and Jeff 2 sets of simulations for the shoreline and Hopkins scenarios. They're at magnitude 6.6 and 7.2. Oh, sorry, 6.6 and 7.2, and they have the 3 simulation methods: XSIM, Grayson-Pitaka, and SDSU. And so this is a plot of the station distribution for the 2 scenarios. And I'm going to, so for each of these stations, there are ground motion predictions from the simulation. And I'm going to plot them on the map as well. So this is how it looks like for PGA. For this is the magnitude 6.6 scenario on the left and the magnitude 7.2 scenario on the right. Plotted against distance. Since these are jumping around a little bit and they're not equally spaced in distances, what I did, I kind of smoothed each simulation by fitting this functional form to each of the simulations individually, and for each of the magnitudes individually. So basically, I'm smoothing through. Oops. Smoothing through here, and I'm smoothing through here. And then I evaluated each of the functional forms, again at magnitudes 1, 2, 3, up to 30 kilometers. And the same thing then, now I have a different grid underlying these. Now I have a grid with two magnitudes, 6.6 and 7.2, and 13 distances. There's one thing we need to...
that's a really important thing. He's got to switch his grid because he don't have the simulations at all of those cases that we evaluated the GMP for. All right? So it's a set that's just focusing now on the bigger magnitudes. All right? So this is going to be an evaluation of where the simulations fall at high magnitudes compared to the GMP.
Yes, it's still the same thing, but we need to be careful not to over-interpret the results, because this is above our second magnitude breakpoint. So this is above 6.5, and so we're only comparing it today to the GMPEs and simulations above 6.5. We could have something that's really weird at magnitude 5, but it would be very, very close at these magnitudes. So it's just one you need to keep that in mind. All right. So I just want to show you one thing here first, and this will show up later. So the XM for 6.6 is really high at really small distances. And this will actually this will show up on the map. So XM will be really, really far away for PGA.
And this is what we were talking about a bit earlier, saying what's happening at XM as you come in close, and that's an important topic for tomorrow or Wednesday.
On the other hand, the other two methods are, you've seen that in one of the earlier plots, are fairly far away at longer periods, at 1 and 2 seconds. And they will show up at different points for the longer periods. Okay, but I'm just going through this now. I hope you can see this. How do I get back? Great.
Let's just do 2 periods, Nico. We'll do peak acceleration and then 2 seconds.
PGA. So here we have, so the map has changed now, but here we have our mean. Here we have the simulation of Scrapes and Pitaka, SDSU, and XM is now outside the range. And that's because it's just really, really high at close distances, but it's actually fairly low at the largest distances I have. And therefore, it has also a really different distance attenuation. And that's just far away from everything else.
The map is rotated. That's what you were asking about, Gabe, is can it rotate? Yes, it's going to rotate, right? But that's not fundamentally an issue.
No, it doesn't. So basically, each map is new because each map I start with a new random initialization, and it's just the distances are now just different than before because I also have a lower dimensional space.
Can you just quickly reiterate? So it's magnitude 7?
It's magnitude 6.6 and 7.2.
And the distance range?
Distance 1 to 30 kilometers.
Okay, thank you.
Right. So on the left, we have again log likelihood. So it's a contour plot of the log likelihood of the data. And on the right is a contour plot of the mean between event residuals of the data. But this is again, so the log likelihood and the mean between event residuals is based on the whole data. So that's based on magnitude 5 to 8, or the largest magnitude we have in there, and distances 1 to 70 kilometers. So this is one period, and let's just go to one of those larger ones, where they are now, I think this is where the two other methods just start to deviate. The green point is actually over here. So it's also the Greiser and Kalka model It's for PGA, it's pretty close to the other models. For longer periods, it also starts to deviate.
You see now that in the simulations, XSIM is near the GMPEs.
Yes.
And grades in PTARC and SDSU are up at the top, right?
Okay, and this is here just a plot of some spectra. And so this is what's going on is that we're at the longer periods, which are here, we're just starting to deviate. Oh, not we're, but some of the two sets of the simulations just start to deviate. And that's just what gets picked up there.
Okay, so I think I'm going to have to stop us, and we'll start again tomorrow on this topic. Is there any final slide you have there that you need to go through?
I mean, I was just going through this one, and then how you could do this.
So let's save this for tomorrow. I think we'll pick this up when we start to talk about the normal faulting for Arizona and go over some of Nico's slides again. But big concept is just the structure of how we're trying to do this, and I want to be sure that it's fun. You have an idea of what we're doing, and we're not just throwing out plots. You have no idea or what's going on. So if you do have questions, this is a good time later on to grab Nico afterwards and ask him about it. I'm going to see Cole and Lisa try to get some of these plots put up tonight so that people could download this presentation and take a look at it and read through it again if you have some questions on the whole thing. So let me interrupt you and stop there, Nico. Thank you. This has really been a huge step forward. We've been at this topic probably for, 3 years now, and we're now getting to the point that I think we know how to do something with it. With that, if you needed a break,